These are the answers to the practice quiz on empirical formulas and molecular formulas. Number 1, if the statement is true, write true. If the statement is false, change the underlined words or number or formula to make the statement true. So letter A, the empirical formula of the compound shown above is CH3N. Well, if we look at the number of carbon, hydrogen, and nitrogen atoms in this molecule, we get a molecular formula of C4H12N2. If we divide each of those subscripts by 2, we get an empirical formula that's going to be C2H6N. So therefore, statement A is false, and you should write C2H6N to correct the underlined portion. For letter B, let's take a look at glucose, C6H12O6, and if we look at the empirical formula, which is dividing each of the subscripts by 6, we get CH2O. Using the periodic table, we can add up the atomic masses of carbon, hydrogen, and oxygen, and we get a molar mass, or a formula mass, for glucose of 180.156. If we do the same for the empirical formula, we get a formula mass of 30.026. So since the formula mass of glucose is actually 6 times larger than the formula mass of the empirical formula, statement B is false, and you should correct the underlined portion with the number 6. In part C, if a compound has an empirical formula of CH2 and has a molar mass of 70.13 grams per mole, its molecular formula is C5H10. Well, the empirical formula is CH2, and that has a mass of 14.026. The molecular formula is unknown to us at the moment, but its molar mass is 70.13. So what's the multiplier to get from 14.026 to 70.13? If we divide the molar mass by the empirical formula mass, that works out to be 5. So therefore, multiplying the empirical formula by 5 gives us a molecular formula of C5H10, so statement C is true. In part D, we have a structural formula. If we count all of the carbons and the hydrogens, we get C11H24. That cannot be reduced, so therefore the molecular formula is the same as the empirical formula. Statement D is true. In number 2, we're given a structural formula for tetrabromocyclooctane, and the molecular formula, if we count all of the carbons, hydrogens, and bromine atoms, is C8H12Br4. We calculate the molar mass by using the periodic table, and we get 427.776. If we break down the mass of carbon, hydrogen, and bromine and calculate the percent by mass for each of these elements, we get 22.5% carbon, 2.8% hydrogen, and 74.7% bromine by mass. So the correct answer for part C is 22.5, again, percent carbon, 2.8% hydrogen, and 74.7% bromine by mass. The next question, what is the empirical formula of this compound? If we divide each of the subscripts by 4, we get C2H3Br for the empirical formula. If the empirical formula of a substance is C2H3Br, then the molecular formula of that substance could be the same as the empirical formula, or we could multiply by 2 and get C4H6Br2. We could multiply the empirical formula by 3, which gives us C6H9Br3. We could multiply the empirical formula by 4, C8H12Br4, etc. So now, in part E, knowing that these are possible molecular formulas, we are simply circling any compound that has the same empirical formula as C2H3Br. So if we analyze each of these compounds, writing down the molecular formula, let's see which of these 6 compounds matches the formulas listed at the top of the page here. So C2H4Br2 for our first structure, that doesn't match anything. C4H6Br2 is one of the possible compounds. Our next molecular formula is C6H7Br3. That doesn't match anything above. We have C6H9Br3, so that does match. And then neither of these final 2 compounds will match. C3H6Br2 and then C4H4Br2. So the only ones that are circled are the ones that match, having the same empirical formula as tetrabromocyclooctane. All right, number 3, fill in the missing information in the table below. Let's start with reducing the molecular formulas that we are given to the empirical formula in the first column. So C15H21N3, if we divide all of those subscripts by 3, we get C5H7N. And then to take 24, 48, and 16, let's divide all of those subscripts by 8, and we get C3H6O2. Now we can use the periodic table to calculate the empirical formula mass for all 4 of these. So starting with CH2O, I got 30.026 for my empirical formula mass. Our next one, C5H7N, I got 81.116 when I added up the atomic masses for those elements. Our next empirical formula has a mass of 74.078. And our final empirical formula in this table has a mass of 41.054. So the next thing we're going to do is take a look at the relationship between the empirical formula mass and the molar mass, or we can take a look at the relationship between the empirical formula and the molecular formula. What is the multiplier that will help us fill in the blanks in this table? Well, for the first example, to get from 30 to 150, that is going to be times 5. So therefore, we take CH2O and multiply each of the subscripts by 5, which gives us a molecular formula of C5H10O5. In our next example, to get from the empirical formula to the molecular formula, we have to multiply by 3. So therefore, we take our empirical formula mass, multiply that by 3, and it gives us 243.348. In our next example, to get from the empirical formula to the molecular formula, we're going to multiply by 8. So therefore, the molar mass would be 74.078 times 8. And if we do that math, we get 592.624. And then finally, 41 and 164. Well, the multiplier there is 4. So we're multiplying times 4. That makes the empirical formula not C2H3N. That now becomes a molecular formula of C8H12N4. And now the table is complete. Okay, moving on to number 4. Fill in the missing information in the table below. So the molar mass of ethane from the periodic table information is 30.068. The molar mass of propane works out to be 44.094. And the molar mass of butane works out to be 58.12. Just adding up the atomic masses for each element. Now to get the percentage by mass, we're going to take, for ethane, 24.02, that's the mass of carbon in that compound, divided that by the total mass, and we get 79.9% carbon. And if we do the calculation for hydrogen, 6.048 grams of hydrogen divided by the total mass, we get 20.1% hydrogen. Now we'll do similar calculations for propane and butane. So for propane, the calculation for percent carbon is 81.7, and the percentage of hydrogen by mass is 18.3. And then finally on to butane. If we run those numbers, we get 82.7% carbon by mass and 17.3% hydrogen by mass. In part B, we are given that compound X is a hydrocarbon and was found to contain the following composition: 60.4 grams of carbon, 12.6 grams of hydrogen. To get the percentage by mass, we'll simply divide each of those masses by the total, which happens to be 73.0 grams. So 60.4 grams of carbon divided by 73 grams total, that gives us 82.7% carbon, and then 12.6 grams of hydrogen divided by 73 grams total, it gives us 17.3% hydrogen. Now these percentages by mass should match either ethane, propane, or butane from the table. And as we can see, they match the data for butane. So we know that the mystery compound, compound X, must be butane because it has the same percent composition. In number 5, we are given the percent by mass for carbon, hydrogen, and oxygen for compound Y, and we have to determine the empirical formula. Now we're going to make the assumption that we have 100 grams of compound Y, and therefore each of those numbers as a percent by mass, that now becomes the mass of the element in grams. So 68.5 grams of carbon, 8.7 grams of hydrogen, and 22.8 grams of oxygen. We are now going to convert from grams to moles for each element. So we get the data from the periodic table. We are not using anything about diatomic elements here. It's simply 1 mole of H, 1 mole of O, because we're focusing on the individual elements within the formula for compound Y. So let's do the math and convert grams to moles. We get 5.70 moles of carbon, 8.6 moles of hydrogen, and 1.43 moles of oxygen. Our next step in the process is to get the lowest whole number ratio of moles. So we are going to divide each number of moles by the lowest value. In this case, 1.43. When we divide 1.43 by itself, we get 1. 8.6 divided by 1.43 gives us 6. 5.70 divided by 1.43 gives us 4. So because these whole numbers are the subscripts in the empirical formula, the empirical formula of compound Y must be C4H6O. All right, the next part of this question is going to have us calculate the molar mass of compound Y. So what do we know in part B? We have a 5-gram sample, and it contains 1.43 times 10 to the 22nd molecules. Now we're given data for grams and molecules, but the molar mass is grams per mole. So we have to get rid of the unit of molecules, and we'll use Avogadro's number on the top in our conversion factor, and then 1 mole on the bottom. If we do this math, we get grams per mole. We need 3 sig figs in our final answer, so we'll round this off to 3 sig figs, 210 grams per mole. Now, we have an empirical formula, and we have a molar mass. Let's use these two facts to figure out the molecular formula of compound Y. The empirical formula is C4H6O. If we add up the mass of the empirical formula, it works out to be 70.088. Now the molecular formula is unknown to us at the moment, but the molar mass is 210. So what is the multiplier to get from 70.088 to 210? Well, that's going to be a multiplier of 3. So therefore we take the empirical formula and multiply by 3. So our correct answer for part C, the molecular formula of compound Y, is C12H18O3. All right, moving on to number 6. Compound Z is a substance that contains the elements carbon, hydrogen, and oxygen. A 25.0 gram sample of compound Z was burned completely in the presence of oxygen gas. The products of the combustion reaction are 58.9 grams of carbon dioxide gas and 16.1 grams of water vapor. Part A, calculate how many grams of carbon were present in this sample of compound Z. Well, all of the carbon that was present in compound Z is now in the form of carbon dioxide gas. So let's start with 58.9 grams of carbon dioxide gas, and let's convert this into grams of carbon. Let's put grams of CO2 on the bottom. Let's put grams of carbon on top, and let's fill in the numbers which come from the data from the periodic table. So 12.01 grams of carbon for every 44.01 grams of CO2. If we do this math, let's round our answer off to 3 sig figs. We get 16.1 grams of carbon. Next, we're going to calculate the mass of hydrogen. Let's take a look at the data from the problem. They told us that there are 16.1 grams of water vapor. Let's convert this into grams of hydrogen. We'll put grams of water on the bottom, grams of H on the top. Again, this is not about diatomic elements here, just individual atoms of hydrogen. We get our information from the periodic table. So 2.016 grams of hydrogen are present in water, and the total molar mass of water is 18.016. If we do this math, this will give us our grams of hydrogen, and that, rounded off to 3 sig figs, is 1.80. So now that we know the grams of hydrogen, we're going to figure out how many grams of oxygen were present in the original 25-gram sample of compound Z. Since we already know that there's 16.1 grams of carbon from part A, and there's 1.80 grams of hydrogen from part B, then the rest of the mass must be coming from oxygen. So we'll take 25.0 grams, subtract the mass of carbon, subtract the mass of hydrogen, and we get 7.1 grams of oxygen. Okay, our next step in the process is to figure out the empirical formula of compound Z. So we know the grams of carbon, hydrogen, and oxygen. We would like to get a simple whole number ratio of moles. So first we have to convert grams of each element into moles. And once we do that math, we can then divide each of the numbers of moles by the lowest number. So for carbon, we get 1.34 moles. For hydrogen, we get 1.79 moles. And for oxygen, we get 0.44 moles. So now we're going to divide each of the moles by the lowest value, which happens to be 0.44. When we do this, obviously we get 1 for oxygen. 1.79 divided by 0.44 gives us 4 for hydrogen. And 1.34 divided by 0.44 gives us 3 for carbon. Since 3, 4, and 1 is going to give us the subscripts in the empirical formula. The empirical formula of compound Z is C3H4O. All right, let's take a look at the calculation for molar mass. We have 25.0 grams of compound Z, and they're telling us it's equivalent to 0.111 moles. So grams per mole is going to be the units of molar mass, and that works out to be 225 if we round that to 3 sig figs. So 225 grams per mole. Now let's combine the empirical formula with the molar mass so we can determine the molecular formula of compound Z. The empirical formula is C3H4O, and if we add up the atomic masses in the empirical formula, we get a mass of 56.062. The molar mass is 225. So the multiplier to get from 56 to 225, that multiplier works out to be 4. So therefore, the empirical formula will be multiplied by 4. And this gives us a molecular formula of C12H16O4. All we have left to do to finish the practice quiz is to write a balanced chemical equation for the complete combustion of compound Z. Let's add oxygen as a reactant, so that's O2. And we know that combustion always gives us products of carbon dioxide and water. I see 12 carbons on the left. Let's put a 12 as the coefficient in front of CO2. I see 16 hydrogens on the left. Let's put an 8 in front of the water. Now, how many oxygens are there on the right? Well, there's 24 plus 8. That's a total of 32 oxygen atoms on the right. So 4 oxygens plus 28 oxygens will give us 32, and the coefficient for O2 works out to be 14. All right, that's it. That's the end of the practice quiz on empirical formulas and molecular formulas. I hope that those answers and explanations were helpful. Thanks for watching, and good luck studying for your quiz.